Okay, so balance and efficiency test of an electric power plant. So the diesel electric power plant. Application of diesel power plant. Diesel power plant is in the range of 2 to 50 megawatts capacity. They are used as central station for small or medium power supply. They can be used as standby plants to hydroelectric power plants and steam power plants for emergency services. They can be used as peak load plant in combination with thermal or hydro plants. They are quite suitable for mobile power generation and are widely used in transportation systems such as automobiles, railways, airplanes, and ships. Nowadays, power cut has become a regular feature of industries. The only solution to the tide of this difficulty is to install diesel generating sets. So this is the layout of a diesel engine power plant. From fuel storage tank, ipapump mo siya. So, siyempre may filter. Discuss natin, di ba? Sa isang subject. Ang pump, pupunta ng data. Then, punta naman sa, may pump naman dito. Yan. Then, ito mga parts na starting air tank. Oil pump. Tapos lubricating oil tank. Oil pump, oil cooler, mga parts yan. Heat exchanger sa cooling tower. Sa raw water pump, makulot sa cooling tower, ikot dito kasi yung heat loss niya. Then, heat loss ng jacket water. Balik doon. Diesel engine. So, ito yung mga parts. Diesel engine or compression, ito. Engine, ignition engines, as they are called, are generally classified in two-stroke and engine and four-stroke engine. And diesel engine, air admitted into the cylinder is compressed, the compression ratio being 12 to 20. At the end of compression, fuel is injected, it burns, and the burning gases expand and do work in that position. So the engine is directly coupled to the generator. So the gases are then exhausted from the cylinder to atmosphere. So remember your power plant is a combustion. So engine starting system. This includes air compressor and starting air tank. The function of the system is to start the engine from cold supplying compressed air. So, fuel system. So, pump draws diesel from storage tank and supplies it to a small day tank through the filter. Day tank supplies daily fuel need of engine. The day tank is usually placed high so that the diesel flows to engine under gravity. The diesel is again filtered before being injected into the engine by the fuel injection pump. The fuel is supplied to the engine according to the load on the plant. Next, the air intake system. Ito, air filter. Hindi siya compress, iba naman to. Air filters are used to remove dust from the incoming air. Air filters may be dye type, which is made up of felt, wool, or cloth. In oil bath type filters, this is swept over a bath of oil so that dust particles get coated. Exhaust system, yun. In the exhaust system, silencer, muffler is provided to reduce the noise. Engine cooling, ito. The temperature of the burning gas in the engine cylinder is the order of 1,500 to 2,000 degrees C. So to keep the temperature at the reasonable level, water is circulated inside the engine and water jacket, which has passage around the cylinder, piston, combustion chamber, etc. Hot water leaving the jacket is sent to heat exchanger. So raw water is made to flow to the heat exchanger, which it takes up heat of jacket water. It is then cooled in the cooling tower and recirculate again. So yan ang system. Engine lubrication. It includes lubricating oil tank, oil pump, and cooler. Lubrication is essential to reduce friction and wear of engine parts such as cylinder walls and piston. Lubricating oil which gets heated due to friction on moving part is cooled before recirculation. So the cooling water used in the engine is used for cooling the lubricant also. What are the advantages? Advantages of diesel power plant. Plant layout is simple, hence it can be quickly installed and commissioned, while the erection and starting of a steam power plant or hydro plant takes a fairly long time. Malaki yun, di ba? Quick starting and easy pickup of loads are possible in a very short time. Location of the plant is near the load center. The load operation is easy and requires minimum labor. Efficiency of part load does not fall so much as that of steam plant. Fuel handling is easier and no problem of ash disposal exists. The plant is smaller in size than a steam power plant for same capacity. Diesel plants operate a high overall efficiency than steam. Yan, note nyo yan. Disadvantages of diesel power plant. Plant capacity is limited to about 50 megawatts of power. Diesel fuel is much more expensive than coal. The maintenance and lubrication costs are high. Diesel engines are not guaranteed for operation under continuous, while steam can work under 25% of overload continuously. Next, the diesel engine power cycle. So nakita nyo na rin ito sa power plant. So the ideal thermal cycle of the diesel engine is illustrated in figure 1. Beginning with the working medium at state 1, it is first electropically compressed to state 2, then heat is added during unlimited isobaric expansion. So straight lang yan, horizontal. Kung mag-lower sa'yo ito matabingi, so hindi na yun isobaric. Kasi pressure and volume. After which, polytropic expansion to the initial volume reduces the pressure to state 4. The ideal work produced by the cycle is represented by its area, and the mean effective pressure is its average height. Polytropic processes 1, 2, and 3, 4 in the ideal cycle are isentropic, with air as the fluid. Thus, for the air standard performance and the gamma is 1.4. Yeah. For ideal cycle, this is isentropic. The ideal air standard efficiency is T is equal to 1 minus 1 over K R exponent K minus 1 times R sub C exponent K minus 1 over R sub C minus 1. The ideal main effective pressure is P sub M is equal to P sub 1 R times K times R sub K exponent K minus 1 times R sub C minus 1 minus R sub C exponent K minus 1 over R sub K minus 1 over K minus 1 where QA is equal to QN is equal to MCP times T3 minus T2. It added. R sub K is equal to R sub C times R sub B. R sub K is the compression ratio. R sub C is the cutoff ratio. R sub B is the expansion ratio. Yeah. So this equation shows that high efficiency is promoted by high R sub K and low R sub C, but that engine size, which may be considered proportional to PM, is increased as RC decreases. So the requirement of adequate fuel combustion imposes a limitation on maximum RC that can be used. Since diesel are load governed by varying point of cutoff, the ideal efficiency increases at part load. This partially offset other tendency and a fairly flat efficiency load characteristic result. So instead of heat being transferred between 2 and 3, fuel is injected into the air and its heat of combustion provides the energy input. The real engine will have non-isentropic compression and expansion processes, which is N is 1.35. Yan, real engine. Pag sabing real, so ito ang method mo. So although equation 1 has its uses in diesel engine studies, the actual efficiencies are considerably less than those of the air standard. Real engine have cylinder cooling for mechanical reasons. Also, they work on an open cycle, meaning that the fluid at the state 1 is not the same as that which completed the previous cycle. The product of combustion of each working cycle are discharged as exhaust gas, and fresh air is inducted for use in the following cycle. So example number 1, an air standard diesel cycle will be analyzed for state of the working fluid and performance. Using the nomenclature of figure 1, State 1 is at 0.9 kilogram per centimeter squared absolute and 27 C. So the volume quantity is that of a single cylinder engine with 25 centimeter bore and 38 centimeter stroke. It will be assumed that after a compression sufficient to produce 538 C, heat is added during the first 10% of the working stroke. So given state 1 is at 0.9 kilogram per centimeter squared and 27 C is one. Single cylinder engine with 25 centimeter stroke and 30 centimeter bore and 38 centimeter stroke. This produced 538 C. Heat added during the first 10% of the stroke is during the first 10% of the stroke. Ito. Yung stroke mo, the first ng B1, B2. So 10% na ito yung 2 and 3. So required analysis of the cycle. Solution. So ratio of compression R sub K is equal to B1 over B2 is equal to T sub 2 over T sub 1 exponent 1 over K minus 1 and P2 over P1 is equal to B1 over B2 exponent K. And T1 is absolute is 27 plus 273 is 300 Kelvin. T sub 2 is 538 plus 270 is 811 Kelvin. T sub 2, asan niya? Sabi niya. After compression, sufficient to produce 538 C. So ito yung compression mo, so kaya ang T2 mo 538. So, 811 Kelvin. So, P sub 1 is equal to 0.9 kilogram per centimeter squared, absolute. So, K is equal to 1.4. So, R sub K is equal to 811. Ito. Over 300 exponent 1 over 1.4 minus 1 is equal to 12. So, compression ratio mo. So, P sub 2 over P sub 1 is equal to B sub 1 over B sub 2 exponent K is equal to R sub K exponent K. Or P sub 2 is equal to 0.9, ito, times 12 is 1.4 is 39.2 kilogram per centimeter squared absolute. Huwag kalimutan. So, meron ka ng P2, T2, and B2. B2 later. So, yan. So, nung makompleto mo yung 1, 2, 3, 4. Then, the piston displacement is B sub 1 minus B sub 2 is pi D squared L over 4. So, D is equal to 25 centimeter or 0.25 meter. L is equal to 38 centimeter or 0.38 meter. Then displacement B sub 1 minus B sub 2 is equal to pi times 0.25 squared times 0.38 over 4 is 0.01865 cubic meter. Now, the clearance volume is B sub 1 minus B sub 2 is equal to R times B sub 2. This is R sub K. Clearance volume is B sub 2. Okay? Wait. So ito, R sub K. So yan. So B sub 2 is equal to 0.01865 over 12 minus 1 is 0.00170 cubic meter. This is now the clearance volume. B sub 2. Then B sub 1 is equal to B sub 1 minus B sub 2 plus B sub 2. Diba? Tama? So therefore, B sub 1 is equal to, itong buo, B sub 1 minus B sub 2 is 0.01865 plus B sub 2 is 0.00170 is 0.0235 cubic meter. Also, B sub 4 is equal to B sub 1 kasi constant volume siya. So this is 0.02035 cubic meter. Ano yung 3? B sub 3. So we know that B sub 3 is equal to B sub 2 plus 10% of B sub 1 minus B sub 2. No. So B sub 3 is equal to 0.0017 plus 0.1 times 0.01865 is 0.003565 cubic meter. Okay. So 3, nakapang T3 sa P3. So T3 over T2 is equal to B3 over B2. So it's equal to 0.003565 over 0.00170 is 2.097. So R is a cutoff ratio. So dito na bago. This is R sub C. Okay. So ito. Then T sub 3 is equal to 811 times 2.097 or 1701 Kelvin. And for the pressure, P sub 4 over P sub 3 is equal to P sub 3 over B sub 4 exponent K is equal to 0.003565 over 0.02035 exponent 1.4. So equals to 0.0873. But P sub T is equal to P sub 2 or 29.2 kilogram per centimeter square absolute. Therefore, P sub 4 is equal to 29.2 times 0.0873 equals 2.55 kilogram per centimeter square absolute. And for T4, T sub 4 over T sub 3 is equal to B sub 3 over B sub 4 is 1K minus 1 is equal to 0.003565 over 0.02035 exponent 1.4 minus 1 or 0.498. Therefore, T sub 4 is equal to 1701 times 0.498 or 847 kilobect. Yan. Ito diba? Yan. So, ito na yung summary. Principal physical state of the circle are summarized. So, state 1, andito yung mga pressure, volume, temperature, and Kelvin and centigrade. State 2, state 3, state 4. So, dyan yung, ito na yung final answer. Okay. Kung may solusyon ka, may value kayo ito, pero walang solusyon. That is mali. Yan. Ideal mean effective pressure is P sub M is equal to P sub 1 times R sub K times K R sub K squared K minus 1 times R sub C minus 1 minus R sub C squared K minus 1 all over R sub K minus 1 over K minus 1. Substitute values. We have 0.9 times 12 times 1.4 times 12 is 0.4, 1.4 minus 1 times 2.097 minus 2.097 exponent 1.4 minus 1, exponent tabi yan. So, divided by 12 minus 1, then 1.4 minus 1. So, P sub M is 5.72 kilogram per centimeter squared absolute. Okay. Derivation tabulator sa thermototal. So, the net work done per cycle is P sub M times P sub 1 minus P sub 2 is equal to 5.72 kilogram per centimeter squared times 100 centimeter per meter squared para naging per meter sir kasi ito 0.01865 cubic meters. So this is now the work. Ang unit mo is kilogram meter is 1067. So alam niyo man ito pag-convert doon sa foot pounds, newton meter, so mako-convert niya. Now the ideal thermal efficiency E is equal to 1 minus 1 over K R sub K exponent minus 1 times R sub C exponent K minus 1 over R sub C minus 1. So E is equal to 1 minus 1 over 1.4 over 12 exponent 1.4 minus 1 times 2.097 exponent 1.4 minus 1 all over 2.097 minus 1. So E is equal to 0.56 or 56%. Yung efficiency tabi, nasa percentage. This is not the answer. Yan. Answer kasi yan ang mga required. Okay. Next, combustion. So, back tayo sa combustion naman. Kailang discussion tayo. Here, the special feature of combustion as carried out in the diesel engine cylinder to receive attention. However, first it appears desirable to repeat and summarize the equation pertaining to fuel oil. We have the density scale. The degree of is 140 over a specific gravity at 15.6 divided by 15.6 minus 130. The degree AP is 141.5 over the specific gravity at 15.6 minus 131.5. Now 15.6C is equal to 65.9. The ignition quality is this. Ito yun, diesel index is 0.018 times degree AP times TAP, aniline point, plus 0.32 times degree AP. So heating value now is Q sub S equal to 41,130 plus 110.6 times degree AP in kilojoule per kilogram. Q sub S is equal to 51,716 minus 8790.6 times specific gravity is squared kilojoule per kilogram and SI. So QL is equal to QS minus 2442.7 times 9H2, the lower heating value. So the hydrogen content is 26 minus 15 times specific gravity percent by weight, where T sub dP is the aniline point and degree C. Okay. Combustion and diesel engine cylinder begins theoretically at the instant injection starts and continues at constant pressure until injection ceases. The distillate fuel used may be considered to have an average chemical formula of C16H32, for which the ideal air quantity is found as follows: C16H32 plus 24O2 is equal to 16CO2 plus 16 H2O. So alam niyo na mag-chemical balance, di ba? So chemistry po yan. So considering the numerical prefixes to be moles, so yung example itong 16, 24, 1. Moles yan. So the equation of combining weight is written as follows. So 224 kilogram of C6H32 plus 24 times 32 kilogram O2 is equal to 16 times 44 kilogram CO2 plus 16 times 18 kilogram H2O. Sa galing yung 224, yung molecular weight ng carbon is 12. So 16 times 12 plus 32 times 1 ng 17. So 224. Yung 32 tabi is, yung O2 is 16 times 2 is 32 kilogram. Yung 44 is molecular weight ng CO2, 12 plus 32. Yan. 18 is yung water, is 2 times 1 plus 16 times 1 is 18. Okay. Since 1 kilogram air provides 0.232 kilogram oxygen, so air per kilogram C6H32 is 24 times 32 over 0.232 times 224 is 14.8 kilogram. So early fuel cutoff is necessary to good thermal efficiency, but early cutoff is not possible with the ideal air to fuel ratio of 14.8. This is due to the need for limiting maximum temperature of the cycle for mechanical and thermal reason under circumstances as set forth in the following example. Yeah. If we use this, so lalabas example mo nito. Yun natin. Example 2. The ideal maximum temperature of combustion of a fuel of 24 degrees up is calculated on the assumption of 427C compression temperature and 14.8 kilogram air per kilogram fuel. So yan. Yan ang fuel ratio niya. Given fuel of 24 degrees up, 427C compression temperature, it's on T2. Yan. So required ideal maximum temperature. Solution, specific gravity, siyempre 141.5 over 131.5 plus degree API or 141.5 over 131.5 plus 24 is 0.91. Then the heating value is QH is equal to 51,716 minus 8790.8 times specific gravity squared and kilojoule per kilogram. So QH is equal to 51,716 minus 8790.8 times 0.91 squared is 44,436 kilojoule per kilogram. Okay, itong ginamit natin. So QL is equal to QS minus 2442.7 H2. So QL is equal to 44,437 minus 2442.7 times 9 times 0.56 minus 0.15 times 0.91. So QL, lower heating value, kasi diesel to, is 41,719 kilojoule per kilogram. That's 2. Itong H2, ito yan. Yan. So during isobaric combustion using CP as 1.0 kilojoule per kilogram, the sensible heat QL will raise the product delta T degrees according to the relation QL is equal to WCP delta T, assuming na yung efficiency 100%. W is 14.8 kilogram plus 1 kilogram fuel, approximately as 15.8 kilogram, approximate lang niya. So delta T is equal to QL over WCP is equal to 41,719 over 15.8 over 1.0 is 2,640 C. Ang taas. So the maximum temperature is equal to T3 plus T2 is equal to T2 plus delta T or 427 plus 2640 is 3,067 C. Since T3 over T2 is equal to V3 over V2 is equal to 1 sub C during an isobaric process. So ito. So R sub C is equal to T3 over T2 is T067 plus 270 over 427 plus 270 is 4.8. So this is high compared to the actual. Not only is the calculated T3 higher than can be considered practical in the engine cylinder, it is high enough so that the thermal dissociation of the product would have prevented its attainment. Furthermore, an R sub C of 4.8 is large enough to impair ideal efficiency seriously. The solution is to use a power ratio higher than the chemical ideal. So assume that 1650C is the limit of T3, then R sub C is equal to T3 over T2 is 1650 plus 270 over 427 plus 270 is 2.75. This is compatible with good efficiency. So W is Q1 over CP delta T is 41,7919. Number 1 over 1650 minus 427 is 34.1 kilogram. Then the L to fuel ratio is 34.1 minus 1 is 33.1. Although this example is based on an ideal engine. So the actual engine is similar. Engine performance. The rapid cycle action in an actual engine modifies the ideal cycle of figure 1. So ito na yung modifications of figure 2. The diagram corners are no longer sharp. Fuel must be injected ahead of dead center, etc. The forms of indicator cards, which are instrument codes, PBs from running engines, are shown in figure 2 for both 2 and 4 cycle types. So this is the 2 cycle and 4 cycle. A diesel engine is used as a source of power which can utilize a relatively cheap fuel. Therefore, its power capacity and thermal efficiency are paramount consideration. So the developed cylinder power is the indicated horsepower, abbreviated as ISP. After engine friction and accessory power needs have been satisfied, the net power available at the engine shop is the brake horsepower, VSP, so-called because it can be, but nowadays seldom is, measured by brake dynamometer. Yan, mas malito sa indicated. So indicated power is difficult to measure directly on a small diesel with great accuracy because the volume of indicator lead through the cylinder head appreciably lowers the normal compression ratio. Yeah. So also, the cylinder heads of the small bore high-speed engine have a special chamber, valves, and other equipment, leaving little or no space available for indicator lead. Since none of these difficulties exist with the large stationary diesel, indicator openings are provided as standard equipment. Hypothetical pressure, known as brake mean effective pressure, BMEP, can be employed to show the magnitude of mean effective pressure. The top pressure, PMEP, is higher on the account of engine friction losses. So ISP is equal to PMEP, LA, and P, over 33,000 and horsepower. BHP is 2 pi WRN over 33,000 horsepower. BMEP is equal to BHP times 33,000 over LAN in pounds per square foot. So in which PMAP is indicated MEP, pounds per square foot, L, piston stroke, bit, A, piston pace area, and so P, number of power stroke per minute. N is equal to is N for 2 cycle and N over 2 for 4 cycle. Check, tandaan nyo to. Pag 4 cycles, hatiin nyo yung N, magiging NP. N is the rotative speed. W is the net dynamometer force, pounds. R is dynamometer arm length, P. So use this equation sa pattern. Doon sa Morse, may error doon ang equation niya kasi ang gamit doon is metric horsepower. Yan. Okay? So huwag niyo gagamitin yan. Pag ginamit niya yun, iba na sagot mo. Okay? Ito na lang gamitin yan. So, kasi mali conversion nila. As is true of all prime movers, there are a number of efficiency expressions applying to diesel. So the mechanical efficiency is the ratio PHP over ISP. Indicated thermal efficiency, S of I is equal to 2545 over WR and Q. Brake thermal efficiency is E sub B is 2545 over WBQ, in which WI and WB is the fuel consumption, pounds per hour, or ISP or BHP. Q is the fuel heating value, meter per pound, either QS or QL according to policy. So example number 3. A 6-cylinder diesel engine on dynamometer test was found to use 38 kg of fuel, having QS of 45,016 kg per kilogram, and a 1-hour test at steady load. So the brake thermal efficiency and the brake MEP will be determined from the following test data and measurement. So the cylinder is 21.6 centimeter and 26.7 centimeter for cycle type. Speed is 600 RPM. Dynamometer torque is 25,000 kilograms centimeter. So given dynamometer torque is 1809 pound-foot. So wait. So ito yung problem example number 3. SI pala yun. So English. So ito. 6-cylinder diesel engine on a dynamometer test was found to use 84 pounds of fuel, having QS of 19,051 BTU per pound, and a 1-hour test at steady load. So the brake thermal efficiency and the brake MEP will be determined from the following test data and measurement. So cylinder is 8.5 inch by 10.5 inch and 4 cycle type. Speed 600 RPM. Dynamometer torque is 1809 pound-foot. So given WR is dynamometer torque is 1809 pound-foot. QH is 19,351 BTU per pound and 600 RPM. D is equal to 8.5 inch or 0.7083 feet. L is 10.5 inch or 0.875 feet. Fuel weight is 84 pounds for cycle type. Required brake thermal efficiency and the brake MEP. Solution. So the brake MEP is 2 pi WRN over 33,000 is 2 pi times 1809 times 600 over 33,000 is 206.7. Then the brake thermal efficiency is NTB is equal to 2545 over W sub B Q, and W sub B is equal to 84 over 206.7. BHP is 0.4064 pounds per brake horsepower hour. So the brake thermal efficiency is N sub TB is equal to 2545 over 0.4064 divided by 19,351 is 0.324 or 32.4%. This is now your answer. So, panalitan ko lang ito. WR is the product of weight and the radius. Brake arm. Okay. Then the brake MEP is 25 BHP times 33,000 over LA and so P in pounds per square foot. So area is 5D squared over 4 times the number of cylinder. N sub P is equal to N over 2 for 4 cycles. So the brake manufacturing pressure is 206.7 times 33,000 over 0.875 over pi over 4 divided by 0.7083 squared divided by 6 divided by 600 over 2 is 10,991 pound per square foot divided by 144 is magiging 76.33 PSI. So the absolute. Well, A. Ano lang yan? Difference na to. Okay. So this is the brake MEP. This is now the answer. Okay. Now for the heat balance, ulitin natin ang heat balance. The energy supplied to IC engine in the form of QH, right? So yan. The energy supplied to IC engine in the form of QH of the fuel input is generally broken down into the following items for heat balance purposes. A, useful work, ito. The actual net shaft output. Cooling is Heat absorbed by water jacket. Sometimes this is not separable from some of the friction in exhaust loss due to merging stream of water that cools cylinder, exhaust manifold, and lube oil heat exchanger. So a WC delta T type of loss. Then the exhaust gas loss. Ito, pangatlo. Heat carried off as sensible and latent heat in the product of combustion. Sensible heat is WC delta T loss. Latent heat is of the form 2442.799 H2 in kilojoule per kilogram. D. Mechanical friction. And then, friction, radiation, dito combined na. So, mechanical friction, crankshaft, and connecting rod bearing, piston, etc. usually taken to include energy supplied to engine-mounted auxiliaries such as pumps, governor, kung may mga sinuplayan ka. Letter E, radiation in unaccounted for. Heat radiated from engine in incomplete combustion loss due to the presence of fuel and exhaust gas. So, item D and E are not open separable nor measurable, so they are usually combined. Then the balance is made by subtracting items A, B, and C from the heat of the fuel and considering the difference to be item D and E. So, andyan yung typical full load heat balance natin in percentage based on QS. Sa auto cycle engine, useful work is 75%, cooling is 30%, exhaust is 37%, friction, radiation, and unaccounted is 8%, input heating value, fuel is 100%. The diesel cycle compression engine, yung useful work is 34%, cooling is 30%, exhaust is 26%, friction, radiation, and unaccounted is 10%. So the input is 100%. Yeah. Okay. So this is the end of diesel engine power plant. Balance topic.